Hi everyone. So this is going to be Math 103 lecture 21. And in this lecture we'll discuss infinite series. So this is chapter 11 in the textbook, which is on series. So what is series? Series is basically taking a sequence and summing up all the elements of this sequence. So in this course, we'll be dealing with infinite series. So we'll be concerned with infinite series. And what does this mean? It means the following. So we start with a sequence. So given a sequence, which we denote in a compact notation by an, where n starts with 1. It could start from 0, for example. In the textbook, the index starts at 0, but for us, the indices will start from 1 in general. And what this means is that the nth term of the sequence is a sub n. So this means that the sequence, the first term is a1, second term is a2, third term is a3, and so on. So given such a sequence, we can try adding up all the terms of this sequence. So in this way, we end up getting an infinite series, which formally looks like this. So I goes from 1 to infinity, a sub I. Because we already know what sigma notation is from chapter 1. So this just means a1 plus a2 plus a3 plus a4 and so on. So it goes forever. So we get a series which is infinite. So intuitively that's what it means, adding up all the terms of the sequence. Before I move on, maybe I should mention that of course the index I here is a dummy variable, right? So this index I here could be replaced by any index. So if you like, going from 1 to infinity, a sub I, is the same as going using the index n, for example, or using the index, I don't know, t. So a sub t. So this is just a dummy variable. But, right, so that's the formal construction of an infinite series. Of course, two fundamental questions arise. First of all, what does this mean? Can we really add infinitely many numbers? That's the first question, right? I mean, I just wrote down symbolically some a1, a2, a3, a4, and these dots seem to suggest that I'm adding all the numbers. But what does this actually mean? And then the second question is if it actually converges to a certain particular number, can we determine that? Like, given a particular sequence, can we determine if this sum is a finite number or if it's infinite? Or maybe it's neither. Maybe it's like oscillating. It's between 1 and minus 1. So let me write down these two fundamental questions. So the first question is, what does this actually mean? So two fundamental questions. So the first one is, how do we precisely define the sum, I goes from 1 to infinity of ai? Because, I mean, can we really add infinitely many numbers all at once? And the resolution of this question is going to involve something called sequence of partial sums. Sequence of partial sums is going to be the key in defining precisely this infinite sum. And the second question is, how do we tell whether this quantity converges or diverges? How do we tell if infinite series, for a given sequence an, how do we know that the corresponding infinite series converges or diverges? And This is a much harder question. In general, it depends a lot on the sequence A sub n, but so partial resolution is that partial resolution of this question is that we'll develop various tests. These are going to be called tests that will tell us oftentimes whether the given series converges or diverges. That will help us obtain the answer. Help us obtain the answer. Okay. So let's go back to the first question. How do we precisely define this infinite sum? Okay. So the question is, let me write again. How do we define the infinite series, I goes from 1 to infinity, of A sub I? Okay. So actually, we've seen similar things in the course so far. When we were doing Riemann integration, we wanted to add up areas of infinitely many thin rectangles. And the way we did that is we first added finitely many rectangles, and then we'll let the number of rectangles tend towards infinity. And in this way, we actually obtained the true area under the curve. This was the main gist of using Riemann sums to compute areas under the curve. We also saw this challenge of adding infinitely many pieces when we were computing mass. Recall that the answer to that was like integrating the density function. There also the trick was to cut up the object that you want to compute the mass of into finitely many pieces, and then compute the approximate mass of each small piece using the density function, and then let the number of pieces go to infinity, and then we take the sum, and that becomes an integral. So here, we were not going to have quite integrals, but I would like to add infinitely many terms, right? I want to add a1 plus a2 plus a3 plus a4 dot 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 forever. Now, of course, that's a really tall order to be able to add all these numbers at once. So the key is add the first 10 numbers, then add the first 100 numbers, then add the first million numbers, then add the first trillion numbers, and just keep going. And then in the limit, as you let the number of terms that you're using to add up tend towards infinity, the limit of that sequence will be the true infinite sum. So the idea is to use sequence of partial sums. Idea to use is sequence of partial sums. Now, what does this mean? So here's what this means. So given a sequence, which we denote by a sub n, we define a new sequence. Define a new sequence, which I'm going to denote by S sub n, capital S, where S is supposed to stand for sum. It's going to be the sequence of partial sums as follows. Okay. So the first term of the sequence, S1, is just going to be the first term of the sequence, A1. The second term of the sequence is going to be the sum of the first two terms, A1 plus A2. So S3 is going to be the sum of the first three terms. S4 is going to be the sum of the first four terms. So as you see, we're just adding the first n terms. That's why it's called partial sums, because you're kind of summing up the terms, but you're partially summing them up. Okay, so if you keep going in this way, S sub n is going to be A1 plus A2 plus A3 dot 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 plus A sub n. And of course, we can also write this as sigma I goes from 1 to n A sub I. Of course, the sequence of partial sums keep going. And then there's Sn plus 1. So this was Sn. And then there's Sn plus 1, and so on. So this sequence is called sequence of partial sums. So this sequence here is sequence of partial sums for the given sequence an. So we started with a given sequence a sub n, and from that sequence we defined a new sequence, which I called sequence of partial sums, and they were defined in this way. So in this way we get a sequence whose nth term is just the sum of the first n terms of the original sequence. Okay. So maybe just to reiterate, we have obtained a new sequence which I've denoted by S sub n, where the nth term of this new sequence is summing up the first n terms of the original sequence. Right? So this is called the sequence of partial sums of partial sums. So yeah, so the way you should think about S sub n is that you're just partially summing up this infinite series. You're just summing up the first n terms. Okay, so what does this has to do with infinite series? Well, we can define the series to equal to the limit of the sequence of partial sums. Right? So in other words, so we define the sum I goes from 1 to infinity of a sub I as the limit of n goes to infinity of S sub n. Okay, so first of all, kind of warning, this limit may not exist. This limit Sn may not exist because the Sn's may not converge. In this case, we say that the series diverges. In this case, we say that the series diverges. Okay, so let's try to understand why it makes sense to define the sum I goes from 1 to infinity a sub I as a limit. So Sn is just adding up the first n terms, and then we're just letting n go to infinity. So this is exactly the intuition that I was trying to convey earlier in the lecture, which is that Sn is just the sum of the first n terms of the sequence. So for example, S sub million is the first sum of the first million terms. So S sub trillion is the sum of the first trillion terms. As you let that number grow, in the limit, you will get this, what represents the sum of all numbers. Okay? So, in other words, note that the limit, just symbolically, limit as n goes to infinity of S sub n is simply limit as n goes to infinity of, well, by definition, S sub n is I goes from 1 to n of a sub I. And so it makes sense to define this as, this is our definition, it makes sense to define this as the sum I goes from 1 to infinity of a sub I. This is exactly what we're saying. We're defining this quantity as the limit of the Sn's. Right? So you can see symbolically it makes sense. Let's look at this equality. Let's stare at it. Here, n is going to infinity, so the top down is going to infinity. So that's why we're getting this infinite series. Okay. So again, so why is it that I was trying to remind us about Riemann sums? It's the same idea. If you want to do something infinite, such as adding up infinitely many terms, the only reasonable way to do it is actually just to add up the first n terms and then let that n go to infinity. Great. So now we have precisely defined our infinite series. So let me recap what we've done. So given a sub n, the sequence, this is our original sequence, we constructed a sequence of partial sums. We constructed this sequence of partial sums, which I called Sn, where Sn is just the sum. I goes from 1 to n of a sub I. Okay. So now we have two scenarios that can happen. So in case 1, this sequence converges. So in case 1, let's say the sequence of partial sums converges. So in this case, we say that our infinite series converges. I goes from 1 to infinity. A sub I converges. And in fact, the value of this infinite series, by definition, is the limit as n goes to infinity of S sub n, which is some number, which is some number. Which is some number. Okay, so I'm just defining what it means for an infinite series to converge. It means that the corresponding sequence of partial sums converge. And when we speak of the value of the infinite series, what we really mean is the limit as n goes to infinity of these S sub n's. And of course, as I mentioned, the sequence of partial sums, these Sn's, may not converge always. In that case, we say that, so this is the case 2. In that case, we say that the infinite series diverges. So that it's possible that the sequence of partial sums, diverges. In this case, we can't really speak of the limit as n goes to infinity of Sn, like this doesn't really make sense. So we simply say that the infinite series, I goes from 1 to infinity of A sub I, diverges. Okay. So this is just definition. So maybe we should give an example to help illustrate what it really means to add infinitely many numbers. And I think the first motivating example is the one of geometric series. Okay, so how does this example work? So let's consider the infinite series given by sum I goes from 1 to infinity of 1/2 to the power of I. So what is this? So we're just trying to add up the numbers 1/2 plus 1/2 square plus 1/2 to the power of 3 plus 1/2 to the power of 4 forever, and we'd like to understand what does this quantity converge to. So note that this example, our example is of the form sum I goes from 1 to infinity of A sub I, where the sequence that we're summing up, well, it's simply 1/2 to the power of I. Okay. So now that we know what 1/2 what AI is, we can actually find the sequence of partial sums. So let's compute the sequence of partial sums. Let's compute for this example. This also illustrates how to compute the sequence of partial sums in practice. Sequence of partial sums S sub n in this case. Okay, so what is Sn in this case? Well, let's do one by one. So let's look at the first term. Partial sums of just involving the first term, so S sub 1 is just the first term of the sequence, which is 1/2. By definition, the second term in the sequence of partial sums is summing up the first two terms, A1 plus A2. Okay, okay, so I guess we don't really need parentheses here, since there's only one term, 1/2. A1 plus A2 is 1/2 plus 1/4, because A2, by definition, is just 1/2 square. A sub 2 is 1/2 square, which is 1/4. And so if you do the math, the arithmetic, that gives you 3/4. Okay, so then let's compute a few more values of sequence of partial sums. So maybe we look at S3. That's A1 plus A2 plus A3. So that's 1/2 plus 1/4, and the third term of our sequence is 1/8. Because by definition, it's A sub 3 is 1/2 to the power of 3, which is 1/8. And when you do the arithmetic, you end up getting, well, let's see. So we have already computed 1/2 plus 1/4. This was exactly 3/4. And now I'm adding 1/8 to it. Well, this becomes 8/6 plus 8/1, which is 7/8. So let's compute S4. A1 plus A2 plus A3 plus A4. So this is 1/2 plus 1/4 plus 1/8 plus 1/16. So again, we have already computed 1/2 plus 1/4 plus 1/8. By the previous line, it's 7/8 plus, now we still have to add the new term 1/16. And if you do the arithmetic, this is 1/16, and this is 14/16. So 14 plus 1 is 15. Okay, so do we see the pattern here? So let's think. So the powers, the denominators that we're getting are powers of 2. So 2, 4, 8, 16. And the numerators are just 1 less than the denominator. So it's 4 here and 3 here, 8 here and 7 here, and 16 here and 15 here. Okay, so if you're not convinced that the pattern will continue, maybe we can do one more term. So S sub 5. This is A1 plus A2 plus A3 plus A4 plus A5. So that's 1/2 plus 1/4 plus 1/8 plus 1/16 plus, we need to add one more term, A sub 5, which is 1/2 to the power of 5, which is 1/32. Okay, so already we computed the sum of the first 4 terms. Sum of the first 4 terms here, we already computed. This is by definition S4, which is 15/16. So you get 15/16 plus 1/32. Again, if common number is 32, so this is 32. If you multiply the top by 2, you get 30 at the top. So this is 30/32 plus 1/32, and that's 31/32. So we see the pattern that the numerator is 1 less than the denominator. So if you continue this way, we get a formula for S sub n, for any n. So S sub n is A1 plus A2 dot 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 all the way up to A sub n. So this is 1/2 plus 1/4, which is just 1/2 square, dot dot dot. Last one is 1/2 to the n. So if you believe the pattern, what you should get is 2 to the n. At the top, you have 2 to the n minus 1. Okay, great. So actually, we just have shown that the nth term looks like this. S sub n is 2 to the n minus 1 divided by 2 to the n for each n, at least 1. And so thus, we can compute the limit. Okay, so I wrote thus here already. So let's compute the limit. The limit as n goes to infinity of the sequence of partial sums, this is just the limit as n goes to infinity of 2 to the n minus 1 divided by 2 to the n. And well, what is this? Okay, so let's split the fraction. 2 to the n divided by 2 to the n divided by 1 minus, so I just split the numerator into two pieces because I have a common denominator. I can do that. And what I get is limit as n goes to infinity. And 2 to the n divided by 2 to the n is just 1. And this is 1 over 2 to the n. And as n goes to infinity, this term here, we'll use some colors, this term here will go to 0 as n goes to infinity, because you're dividing by larger and larger numbers, so the answer is 1. Because you get 1 minus 0, so it's 1. So we just showed that the sequence of partial sums is 1, and so limit as n goes to infinity of Sn is 1, which means, so this implies that the sum that we were interested in originally, I goes from 1 to infinity, of 1/2 to the power of I, by definition must converges, because remember, the definition of an infinite series converging means that the sequence of partial sums converge, meaning that they have a limit. So limit as n goes to infinity of Sn exists, and in this case it's 1. And in fact, we said that if the sequence of partial sums converge, namely that the Sns have a limit, we said that the infinite series converges, and moreover, the value of the infinite series, I goes from 1 to infinity of 1/2 to the power of I, is equal to the limit of the Sns, by definition of this. So this is limit as n goes to infinity of Sns, so it is 1. Okay, so we determined the value of this particular infinite series. So the conclusion from the above analysis is that the sum I goes from 1 to infinity of 1/2 to the power of I, sorry, let me just write it a little better, 1/2 to the power of I, this is just 1. Okay, so once again, the index I here is just a dummy variable. And you could have also written n goes from 1 to infinity of 1/2 to the power of n, or any other letter instead of I. Okay, so we kind of obtained the answer, right? But let's give a geometric intuition as to why this makes sense. So pictorial proof, if you like, a picture proof. Proof by picture. And I think this is extremely convincing if you've never seen this particular picture before. And personally, I think when I first was learning about geometric series many years ago, this was the first picture that convinced me that it makes sense to add, infinitely many numbers. And this picture represents why the answer should be 1 for this particular example. Okay? So let's draw a segment of size 1. This is 0, this is 1. Okay? Now, let's divide it in half. If we divide the segment in half, then the length of this piece is just 1/2. Because the total, so think of this as a rope. You have a length rope, length 1 rope, and I'm just cutting the rope in half, taking this piece. That's 1/2. Now, the remaining rope has also length 1/2. I can also divide that in half, and this piece will then have length 1/4. Now, the remaining piece also has length 1/4, so you can divide that by half, and I have 1/8. Now, the remaining piece has length 1/8. I can divide that by 1/2, and then take the first piece of that, and that should have length 1/16, and we can keep going. So divide, take the first piece, 1/32, and so on. Just repeat this process. So, repeat the process. What is it that we end up getting? So we end up getting, let's see, 1/2. That's the size of the first half of the strip or rope. Then I have 1/4 for this piece. Then I have 1/8 for this piece. Then I have 1 over 16 for this piece, 1 over 32, and so on. I have to keep going forever. Well, if you continue this process forever, in the limit, you will exhaust the length of the entire rope. So the answer should be 1, because you exhaust, because in the limit of this process, we exhaust the entire interval. We get everything, the entire interval. So that's it. That shows that the sum of these numbers is 1. Entire interval, which I've been thinking of as a length 1 rope or string. So that's a proof. So thus, sum I goes from 1 to infinity of 1/2 to the power of I is 1, right? Because if you expand what the sigma means, you get exactly the sum above. When I is 1, you get 1/2. When I is 2, you get 1/4, and so on. Okay, so we have already given 2 justifications for why the sum of this particular infinite series should be 1. The first justification involved looking at partial sums and computing the sequence of partial sums explicitly and taking a limit of the sequence of partial sums and getting 1. And the second proof was just looking at the picture and kind of cleverly dividing the interval from 0 to 1 iteratively into pieces by dividing it by half each time. And there's actually a third way to justify this, which is just using a formula. So finally, we can also use formula for the geometric series. So this is a little bit of a cheap way because we're just using the formula, and how do we even prove the formula to begin with? And you can prove the formula actually in general using the sequence of partial sums method, this method. But we all know the formula, so let's just use it. So what was the formula? So we get sum I goes from 1 to infinity of 1/2 to the I. Well, the formula for the sum of geometric series is a divided by 1 minus r. So where a is the first term, this is only valid for the geometric series. Okay, so this formula only makes sense if you're summing up geometric series. So the formula is a divided by 1 minus r, where a is the first term and r is the common ratio. Okay, so in this case, the first term, so what's the first term? Well, the first term corresponds to the case when the index I is equal to 1. So in this case, it's 1/2 to the power of 1, which is 1/2. That's our first term. And the common ratio, not ration, but sorry, ratio, is 1/2, because that's the term whose powers were taken. Now, this formula is only valid if the absolute value of r is less than 1. So in this case, the absolute value of r is 1/2, which is indeed less than 1. So we can use this formula. So we get, okay, so what do we get? We get 1/2 for a, and 1 minus for r, we also have 1/2. So we get 1/2 divided by 1 minus 1/2 is 1/2. So 1/2 divided by 1/2 is 1. So again, check mark. We get the same answer. We get the same answer of 1 as before. Great. So next thing that we should discuss, maybe summarize. Next thing we should do is to summarize what we know about geometric series. So we actually have already discussed the geometric series in chapter 1. So we have actually seen infinite series in some sense. And the key result to remember, the key result is the following. If you look at the sum, n goes from 0 to infinity of a times r to the n, is a divided by 1 minus r if the absolute value of r is less than 1. And if the absolute value of r is not less than 1, which means it's at least 1, then this series diverges. Okay. So now, I think it might be worthwhile to think about this result again in the particular case when the common ratio R is 1 and minus 1. So let's just think about let's think about this result. This will give a greater insight for the sequence of partial sums, I believe, about this result above. Actually, let's just do the case when A is 1 and R is 1. That's kind of the first case. And also, so maybe this is one case to consider, and also the case to consider is A equals to 1 and R is equal to minus 1. So I think understanding what happens in this case will be insightful. Well, we already know what the answer is, right? Because in both cases, case 1 and case 2, it's a special case of this result. So it certainly falls into onto this result because you're in the second case. So when R is 1, you're in this case. When R is minus 1, the absolute value of R is still 1, so you're in this case. So we know what the answer is for the series. It diverges. But can we see it plainly that it should diverge? That's what I want. I want us to build some intuition for these things. So let's think about case 1. So in this case, A is 1, so just have 1. So R to the n, 1 to the n. And so n goes from 0 to infinity. Yeah, so notice one thing about geometric series. This formula is valid when n is 0. It starts at 0. Because basically you want the first term to be a, and that's when n is 0. So when n is 0, we get a times r to the 0, which is a. So if the index doesn't start at 1, if the index doesn't start at 0, it starts at 1, then this formula still works as long as you interpret a to be the first term. But it's not going to be this a. In that case, yeah, it's the first term. So anyways, we have seen enough of geometric series already in chapter 1. But we should, why is it that this should diverge? Well, let's just think about this. This is, n goes from 0 to infinity of 1 to the n, but 1 to the power of n for any n is just 1. So you're just saying 1 plus 1 plus 1 plus 1, blah, blah, blah. This should definitely diverge because you just keep adding a bunch of 1s. How could that ever lead to anything that's convergent? Now, of course, let's think about the sequence of partial sums in this case, right? Let's start with S0. So S0 in this case is A0, which is just 1. S1 is in this case is A0 plus A1, so it's 1 plus 1. That's 2. And so you just keep going. S3 is just A0 plus A1 plus A2, so it's 1 plus 1. I'm sorry, this should be S2. S2 is A0 plus A1 plus A2, so it's 1 plus 1 plus 1, so we get 3. So basically, okay, so you're just adding a bunch of 1s. So Sn is just adding up A0 plus A1 dot 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 plus A sub n, which is just 1 plus 1 dot 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 plus 1, and n plus 1 times, because I start at 0. So there's n plus 1 copies here. So you just get n plus 1. So in this case, our sequence of partial sums, Sn, this is just a sequence m plus 1 for each value of n. So, and this sequence certainly diverges. This diverges. Because the limit, as n goes to infinity, the limit as n goes to infinity of n plus 1 certainly is infinite. So this is just a formal way of justifying what I was saying here, which is just adding a bunch of 1s should diverge. Okay, so let's think about the case r equals to minus 1 case. So in this case, the geometric series is n goes from 0 to infinity of minus 1 to the n. So this is, okay, the first term is negative 1 to the power of 0, so that's 1. Next term is negative 1 to the power of 1, that's -1, and then you have +1, -1, +1, -1. Okay, so this presumably diverges, right? Because that's what this result says. This general result, the key result, tells us that when r is -1, you're in this second case, so you should diverge. So how can we see from the sequence of partial sums, how could we see from the sequence of partial sums that this should diverge? How can we see from the viewpoint of sequence of partial sums that this series above should diverge? So I think doing this example in detail is, I find it illustrative. So the sequence is -1 to the power of n. So in this case, the sequence that we have in mind is of the form sum n goes from 0 to infinity of -1 to the power of n. So it's of the form an, where nth term is just -1 to the power of n. So let's compute the sequence of partial sums for this. Let's compute the sequence of partial sums. So S0, we start at 0, so we have to do S0, is just A0, which is -1 to the power of 0, which is 1. S1 is by definition A0 plus A1. And so this is 1 minus 1, which is 0. S2 is A0 plus A1 plus A2. So it's 1 minus 1 plus 1. So 1 minus 1 is 0, plus 1 is 1. So what's the pattern? So S3 is A0 plus A1 plus A2 plus A3. So this is 1 minus 1 plus 1 minus 1. So this is 0. So they actually alternate 1, 0, 1, 0. So in fact, Sn is, it's either 1 or 0 depending on the index. If n is, let's see, so for even numbers, 0, 2, 4, it's going to be 1. And for odd indices like 1 or 3, the answer is going to be 0. So sorry, if for the first case, if it's 1, if n is even, and 0 if n is odd. Okay, so that's it. We found our sequence. So thus, the sequence of partial sums is, so I think I made a little typo here. This should be n starting at 0 right here. Let me make sure that I don't have that typo here. Earlier, also here, the small typo. This should be n starting at 0 because we start the geometric series at 0. Sorry about that. Let me just see. Okay, looks good. Okay, so going back, we have shown that the sequence of partial sums for this infinite series here is 1, 0, 1, 0, 1, 0, dot, dot, dot. And this sequence above, this sequence of partial sums, certainly diverges. Because it's a sequence of alternating 1s and 0s, it oscillates. And oscillates between 0 and 1, and so it should diverge. And that's the reason why, therefore, the original series I goes from 0 to infinity of -1 to the power of I diverges. Okay. So I just justified to you why this diverges from the viewpoint of sequence of partial sums. Of course, you already knew that this infinite series diverges because it corresponds to the case when r is -1, and according to the key result above, when r is -1, it should diverge. Also, I should add one more thing. Here I want to add in red, I require this number to be not 0. I want to add this requirement. Because if a is 0, then everything is 0 and it converges for every value of r. So I want to get this part. I want to get it diverges when r is at least 1. Yeah, if the absolute value of r is at least 1, we know it diverges. And for this to be true, I need the initial value a to be not 0. Because if a is 0, then everything is 0. Okay, but that's not really interesting in any case. Okay, great. So now the next thing we're going to discuss is one of the most interesting series called Harmonic Series. And it's the following series, okay? So let's consider the following series. Sum n goes from 1 to infinity of 1 over n. Okay, so this is adding up the following. So when n is 1, you get 1 divided by 1, which is just 1, plus 1 over, the next one is when n is 2, so the next term is 1 divided by 2, plus 1/3, plus 1 over 4, plus 1 over 5, plus 1 over 6. Okay, so the terms are getting smaller and smaller and smaller, right? So the question is, does this series converge? And the answer is that this series diverges. That's not at all clear, I should say, right? So first of all, the fact that the terms are getting closer and closer to 0 turns out doesn't help in this case for convergence. So later on in this lecture, I'll discuss something called the Divergence Test, where this particular example will be very relevant, because this is going to be an example where the Divergence Test cannot be applied, because the terms of the sequence tends to 0. So it's unclear, right? 1 over n tends to 0, so it's unclear if this infinite series converges or diverges. It's not at all clear what happens. But I will prove to you that in fact this sequence diverges, but we need an intricate argument to see this. So the theorem is that the harmonic series diverges. This harmonic series, which is this series here, diverges. Okay, so let me prove it to you. So there's in the book you can find at least 2 proofs, and this is one of the proofs, and this is sort of the standard proof. And it's a really neat idea. It's about cleverly grouping terms together. Okay, so here's what we're going to do. So observe that. So I think this really is a nice trick to remember, and it's also somehow one of a kind type of thing. So seeing this once in your lives, I think it's a good experience. So the thing we're interested in is summing up 1 plus half, right, plus 1/3, okay, plus 1 over 4, plus 1, I'm going to write a lot of terms, 1 over 5, plus 1 over 6, plus 1 over 7, plus 1 over 8, plus 1 over 9, plus 1 over 10, plus ... Let me write 1 over 16 here. It's going to be important. Okay, I think this is probably enough, so ... This is the thing we're interested in, right? To understand what does this sum look like as n goes to infinity, as you add more and more terms. We want to understand whether this sum converges to a finite number or not. And of course, our claim is that the harmonic series diverges. In fact, that if you keep adding this forever, it will grow bigger and bigger and bigger. It will never reach a finite number. In fact, it will grow unbounded. Okay, so the trick is the following. So let me use a different color. So the trick is to actually group terms as follows. So let me group 1/3 with 1/4. Let me group from 1/5, 1/6, 1/7, 1/8 together. So the first, so the 1 is very special, so let's forget about 1. So you have 1/2, that's a group of its own, I guess. Okay, let's feel like this is like a group of its own. Then I have a group of 2 terms, 1/3 plus 1/4. Then I have a group of next 4 terms. Then I have a group of next 8 terms, and so on. We keep adding more and more groups, but in sizes that are powers of 2. Then I make the following observation. Okay, so 1/3 is at least 1/4, right? And this is, so I'm going to match this with this. Well, actually, it's bigger, so let's just write strict. So it's bigger than, certainly bigger than 1/4 because it has a smaller denominator. Now let's look at 1/5 and 1/6 and 1/7. Each of them is bigger than 1/8, right? So each of them is bigger than 1/8. Certainly. Because they have smaller denominators. 5, 6, 7, they're all less than 8. So 1/5, 1/6, 1/7, they're all bigger than 1/8. Similarly, let's look at 1/9, 1/10, and so on. All these numbers, they're at least, they're bigger than 1/16. They're all bigger than 1/16. They're all bigger than 1. So the one that comes before it is 1/15. That's also bigger. So all these numbers is bigger than 1/16. Okay, well that means that this entire sum under consideration, which is the harmonic series, because I'm going forever, is certainly bigger than 1. It's this one. Oops, sorry. Bigger than 1 plus half. I didn't do anything to the half. Now plus 1/4 plus 1/4, because 1/3 is bigger than 1/4, so I can replace this 1/3 with 1/4 because I'm putting a greater than sign here. And certainly I can also replace 1/5, 1/6, 1/7 with 1/8. So this quantity here in the group, in this group, is bigger than 1 plus 8 plus 1 plus 8 plus 1 plus 8. Sorry, 1/8 plus 1/8 plus 1/8 plus 1/8. And similarly, each of these terms, now there are 8 terms here, and each of them is bigger than 1/16. And, well, the last one is exactly 1/16. And the pattern continues, okay? Okay, so if you're unsure what the pattern continues, let's write if you like. So so here we had kind of 8 terms. Oops, let me just write it a little better. So here we had 8 terms. So if you want to see the pattern, well, it's going to be 1/32, dot, 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 1/32, and so on. And here we're going to have kind of 16 terms. Okay, so what's the punchline? Well, let's look at these quantities, right? So these quantities, so what is this equal to? So the thing we were interested in was the harmonic series. I just showed that the harmonic series is bigger than this new series that we have. Well, what is this series? So we have 1 plus a half. You have 2 divided by 4, right? Because you have 2 copies of 1/4. Here we have 4 copies of 1/8, so we get 4/8. And then here, right here, we have 8 copies of 1/16, so we get 8 divided by 16. And here we have 16 copies of, this keeps going, 16 copies of 1/32. So if you add 1/32 to itself 16 times, you will just get you will just get 16/32. Dot, dot, dot. It keeps going forever in this pattern. Okay, well, what is this? This is just 1 plus a half. This is also a half. 2 divided by 4 is a half. 4 divided by 8 is a half. 8 divided by 16 is a half. 16 divided by 32 is a half, and so on. Okay, but this last series, I'm just adding a bunch of 1s, right? This diverges, certainly diverges. because I'm just keep adding 1/2, right? This portion here, this is just sum. I goes from, I don't know, 1 to infinity of 1/2. So I'm just adding a bunch of 1/2s. And this is infinity. Okay, so that's it. We have shown that the harmonic series, which is what we're really interested in, is bigger, it's bigger than something that's already infinite. So we conclude that the harmonic series itself must be infinite. Because how else can you be bigger than something which tends towards infinity? So, let me just write down the punchline. So since we showed that the sum n goes from 1 to infinity of 1 over n is bigger than some series which already diverges to infinity, some series which already diverges to plus infinity, we conclude that the same should hold. This is basically a comparison test. We conclude that n goes from 1 to infinity of 1 over n also diverges. And that finishes the proof of the claim that the harmonic series sum, let's write this a little better, sum n goes from 1 to infinity of 1 over n also diverges. So at the last step of the argument, we used something called the comparison test, which we have seen already for integrals. It's the same thing here. We use comparison. If you're bigger than something that diverges, you must diverge. And later we'll also discuss if you're smaller than something that converges, and if you're positive also. If you're positive and you're smaller than some series that converges, then you must also converge. And that's the other version of comparison. But certainly, if you're bigger than something that converges to infinity, you certainly must also diverge towards plus infinity. Okay, so so here's the thing. So we just showed, we just proved, not just showed, but we just proved that the sum n goes from 1 to infinity of 1 over n diverges. Okay, but then it's very natural to ask about a similar series, right? So what about, for example, what about, I don't know, n goes from 1 to infinity of 1 over n squared? Does that converge or does that diverge? In other words, we're just asking, right? In other words, we're asking if you keep adding the terms 1, so that's the case when n equals to 1 is 1 over 1 squared, which is 1, and then 1 plus 2 squared divided by 1 plus 3 squared plus 1 plus 4 squared, dot, dot, dot. We're asking if this series converges. We're just asking if this converges or diverges. If you just keep adding these terms, do they converge towards a finite limit, or do they kind of escape towards infinity? Now, notice that here you're squaring, so these numbers are actually smaller. They're even smaller than adding 1 over n. So it's not really clear here if should this diverge or converge just by knowing information about this one. And it turns out, in fact, that this series, sum n goes from 1 to infinity 1 over n squared, actually converges. Turns out that the sum n goes from 1 to infinity of 1 over n squared converges. So this already shows, I mean, there's something subtle about convergence and divergence of infinite series, because I mean, if you just look at these two series, right, I mean, they look very, very similar. This is like summing up 1 over 2, 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And this is summing up 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. And somehow the second one, the terms are small enough that the sum actually converges to a finite value. Even though in both cases, like 1 over n and 1 over n squared, in both cases, those terms are getting smaller and smaller. In fact, the limit of both of them are 0 as n goes to infinity. So the terms that you're adding at each step, they are decaying. They are becoming more and more negligible. But somehow for 1 over n squared, they really are negligible in the long run so that the series converges. However, for 1 over n, it's significant enough that the sum of the terms diverge towards infinity. Now, this fact we will prove. Okay, so we will prove this fact. We will prove, in fact, in this lecture, I'll give an elementary argument, prove this fact later in this lecture. So rest assured. But let me go on a side and mention a very, very fun fact that was proved by Euler a couple hundred years ago. So Euler proved an amazing identity regarding this sum. So what he showed is that this sum, n goes from 1 to infinity, of 1 over n squared, right? So this is 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, like this thing. That's equal to this. This sum actually, well, we know it converges according to this fact, but he showed that this converges to a very special number. This is pi squared over 6. I think this is amazing. How does pi show up here, right? It's very mysterious. So this is highly non-trivial fact, which we will not prove in this course. We don't need this. We don't need this result, and we won't ever refer to it. But I thought I would mention it. So I'm just making sure that people aren't worried about seeing something like this in this course. But we don't need this result in this course. But I think it's certainly worth mentioning. But somehow summing up the reciprocals of the squares of the natural numbers in the limit, that sum ends up being pi squared over 6. So somehow shows the universality of the number pi showing up everywhere in math. And this is one occasion. Okay, so somehow there's multiple ways to prove that this sum converges, and we'll see later in the course, maybe next lecture, something called the integral test that will help us prove that this converges by comparing it to a certain integral. But I want to give a slightly different proof that's more elementary, and there's a good reason why I'm doing this, is because it will introduce us to a concept called telescoping sums, which is absolutely part of the course content. Telescoping sums appears in the textbook, and it's very prevalent in math, and you should definitely expect to see it in the exams. So telescoping sums is a particular sums infinite series. So I should say telescoping sums or series, for which, when you compute the sequence of partial sums, there's a massive amount of cancellations. Okay? So some infinite series, some series, have very nice cancellations when you compute their partial sums in their partial sums. So these are often called telescoping series. These are often called telescoping series. Okay, so let's give an example of this. So, example. Let's evaluate the sum I goes from 1 to infinity of n times n plus 1. Okay. So the trick here, first of all, we can actually show that this series converges, and we'll compute the actual value. And here's a nice solution. Here's a nice trick, is they use partial fraction decomposition. So let's write this command. This is the thing that we're trying to add up. 1 divided by n times n plus 1. So you can check, I'm going to leave this verification to you, that this is equal to, I mean, we can just check by just looking at it. I mean, common denominator is n times n plus 1, so this is going to get an n plus 1 on top, and this is going to get n on top. N plus 1 minus n is 1. Anyways, this is just basic algebra, and this is exactly the partial fraction decomposition, which you have plenty of experience when we dealt with integration techniques. This is the kind of thing that you're familiar with applying. Taking this and writing, a divided by n plus b divided by m plus 1, and solving for the constants a and b. And in this particular case, a is going to be 1 and b is going to be minus 1. Now, why is this nice? Well, it's going to make it easier to compute the partial sums. There's going to be a lot of cancellations. Okay? So what do we have? Well, the partial sums for this series, n goes from 1 to infinity of 1 divided by n times n plus 1. Well, this is equal to, so however, we know that now 1 divided by n times n plus 1 is just 1 over n minus 1 over n plus 1. N goes from 1 to infinity. Just move out a little bit. Easier to see. Great. Okay, perfect. So for this sum, we can compute the sequence of partial sums. So let's look at S1. S1 is just the first term of this series. So this is the case when n is 1. So you get 1 over 1 minus 1 over 2. Okay, so let's leave it at that. The second partial sum of this series, S2, is, well, it's the summing up the first two terms. So summing up when n is 1 and when n is 2. So when n is 1, the first term here is 1 divided by 1 minus 1 divided by 2. Okay? And then plus, now we have to add the term that corresponds to n equals to 2, and that is 1 divided by 2 divided by 1 divided by 3. Because that's what happens when you plug in n equals to 2. Okay, but we already see some cancellation. Look at 1/2, negative 1/2 plus 1/2 cancels. So you just actually get 1 minus 1/3. So let's look at S3. So now I have to add up the first 3 terms. So the first 2 terms I've already computed above, and my term corresponds to n equals to 3 is the case when I plug in n equals to 3 into this formula. So I just get 1/3 minus 1/4. So 1/2 gets canceled, 1/3 gets canceled. Notice that there's a negative 1/2 plus 1/2, negative 1/3 plus 1/3. They get canceled. And so you just get 1. Remember, this 1 survives, and then minus 1/4 survives. Okay, seems like we're getting a nice pattern. Yeah. So let's do one more example just to be sure. S4 is 1 divided by 1 minus 1/2 plus 1/2 plus 1/3 plus 1/3 minus 1/4 plus, now I have to add the term corresponds to n equals to 4, and that's 1/4 minus 1/5. And so again, lots of cancellations happen. These cancel, and so you just get 1 minus 1/5. Okay, so we see the pattern, right? So the pattern is that, keep going, the nth term is going to be, or let's call it the kth term, maybe, not to be confused. So also to be used to the notation of using other dummy variables. So S sub k is adding up the first k terms of this particular series. And so I'm just getting this. So the last term is going to be 1 over k minus 1 over k plus 1. Because this is the term that corresponds to when, this is the term that corresponds to the kth term of the sequence. Kth term of this sequence. That's when you get 1 divided by k minus 1 divided by k plus 1. And we see, just by looking at the previous 4 lines, we see that cancellations happen. And so in fact we get, they all cancel. And this 1/3 gets canceled with something here, and this 1 over k actually cancels out with something that came before. So you actually just end up getting this one that survived minus 1 divided by k plus 1. And so we have shown that the sequence of partial sums sk, where k starts at 1, satisfies the formula, a really nice formula, that sk is just 1 minus k plus 1. 1 minus 1 divided by k plus 1, right? So we already saw the pattern here. So when you have 1 here, you get 1 minus 1/2. This is 1 minus 1/2. For S2, we get 1 minus 1/3. For S3, we get 1 minus 1/4. So for S4, we get 1 minus 1/5. So this number is always 1 more than the index. So that's why S sub k is 1 minus 1 divided by k plus 1. And this is a very nice sequence. And note that this sequence converges. Limit as k goes to infinity of sk is the limit as k goes to infinity of 1 minus 1 divided by k plus 1. Well, this term here, this goes to 0 as k goes to infinity, because you're dividing by bigger and bigger numbers. So, okay, so what do we end up getting? Well, we end up getting that the limit of sk's is just 1. So this limit is just 1 minus 0, which is 1. So as a result, the original series that we had in mind converges, and it converges to 1. So the original series we had in mind was n goes from 1 to infinity of 1 divided by n times n plus 1. This converges. And in fact, we showed, and in fact, it converges to 1, because by definition, the infinite series, if it converges, it must converge to the limit of the SNs, or limit of the SKs, as k goes to infinity, because that's a simple definition of an infinite series. So this is in fact 1, this one here. Okay, so we evaluated the sum, which was exactly what the question was asking, right? The question was asking us to evaluate this infinite series, and we conclude that this infinite series is in fact 1, equals to 1. And so now we're in a position to actually prove what I claimed earlier, so a theorem, which is that the infinite series, n goes from 1 to infinity, of 1 over n squared converges. Okay, so the proof is going to be an application of a comparison as follows. So note that, so first of all, everything is positive. All the terms are positive. So certainly all the terms are positive because you're just adding 1 over n squared. And so we know that it's at least positive. And let's note that this is 1 plus the sum. N goes from 2 to infinity of 1 over n squared. Okay, so what did I just do? Well, I just split the sum into 2 pieces. I just split off the term that corresponds to n equals to 1. Right? So this is just 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, dot, dot, dot. So I just wrote it as 1, which corresponds to the term 1 over 1 squared. And then I have the rest of the terms here. That's why I'm starting at n equals to 2 here. So this portion is the rest of the sum. So it starts with 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on. The reason I did that is because now I'm going to shift the index as follows. So I'm just going to keep going here. So I'm just going to keep writing underneath. So this is equal to 1 plus sum. N goes from 1 to infinity of 1 divided by m plus 1 squared. Okay, so how do I go from this line to this line? Well, this is just shifting an index. Okay, we're just shifting an index. So if I shift the lower index to 1, so if I have to start at 1 now instead of at 2, then I have to upshift this n to m plus 1, right? So that's the general rule of shifting an index. If you're going to shift the index that appears on the sigma by 1 down, then you have to shift all the n's that appear inside, outside the sigma, right here in front of the sigma. You have to upshift it by 1, shift it up by 1. Now, certainly that's intuitive, because if you just look at these two sums, they're the same thing, right? These two are the same thing. So this and this, they're the same. Namely, they're just 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared forever, right? Because, like, let's look. When n is 2, you get 1 over 2 squared. When n is 3, you get 1 over 3 squared, and so on. And here is the same thing. Even though you're starting at n equals to 1, the terms you're adding is 1 divided by 1 plus 1 squared for the first term. And then when n is 2 here, you get 2 plus 1, which is 1 over 3 squared. And so, in fact, we do have the same infinite sum. Okay. Now, why did we do it this way? Because now I can use comparison as follows. So this is less than, I guess I don't know if I need color here. So maybe I'm just going to use the regular ink. So this is less than 1 plus. Now I want to make my sum here bigger, right? I need to make all these terms bigger. I can make it bigger as follows. Instead of writing m plus 1 squared, I can write n times m plus 1. This sum is bigger than this sum because this term here right here is bigger. This term here is bigger than this term because the denominator of this term, n times m plus 1, this denominator, is actually smaller than the denominator of m plus 1 squared. Right? So going from here to here, maybe I'm going to use color. Going from here to here, we used the fact that the denominator, m plus 1 squared, denominator of this one is certainly bigger than n times m plus 1, because here I'm multiplying m plus 1 with n plus 1, but here I'm multiplying n with n plus 1, and so that actually means that 1 over m plus 1 squared, if you have a bigger number in the denominator, it's smaller. 1 over n, 1 divided by n times n plus 1. Okay. What's the advantage of this? Well, the advantage is that, this we have already analyzed. This already converges. This one already converges. Okay. So that's it. We have shown that the series that we're interested in is smaller than something that already converges. So we have already shown this converges by a previous example. That was this example here. And so by comparison, since 1 over n times m plus 1, n goes from 1 to infinity, converges. Since this converges, as we have shown before, using the idea of telescoping sums, we conclude that the sum 1 over n squared, where n goes from 1 to infinity, also converges. once again, that's because we showed that the series we're interested in has positive terms inside and is less than some other series that converges. Great. That's good. So so far we've only seen two things about these series of this type. We've shown that the harmonic series diverges, and we've seen that the series 1 over n squared, as n goes from 1 to infinity, we've shown this converges. These are two separate results that we have proved in this lecture. So that's one result, and that's another result. Okay, so it's natural to ask what happens if this power is not 1 or 2, but some other it's not 1 or 2, but some other number, and here's a general result that you need to know. So the general result that it's good to be familiar with is that the sum n goes from 1 to infinity of 1 over n squared, n to the p, for any p is any real number. So this converges for p bigger than 1. Okay? And diverges for p at most 1. Okay? Now this result is actually very similar to something you've seen before for integrals, right? This should remind us of the following result that we have seen before, which is that the integral from 1 to infinity of x to the p is this thing converges for p bigger than 1. So integral of 1 over x to the p dx converges for p bigger than 1 and diverges for p at most 1. And so these results kind of look very similar to each other. They have the same format. Here we have an integral, here we have a sum. It turns out that this is not a coincidence. In fact, we will see something later. We'll connect these two results using something called integral test. These two results. So this is coming up next, something called integral test. And in fact, what we're going to do is we're going to use this information about the integrals, which we know, because we know that this integral converges and diverges. We proved it. We've shown that this integral converges for p bigger than 1 and diverges for p less than or equal to 1. We're going to use this result to prove the result about the series. So we're going to use integrals to prove something about infinite series. That's the content of the integral test. So let me end with kind of answer to the question that I originally, one of the fundamental questions in the beginning of the lecture, which is that how do we tell if a series converges or diverges? So as I said, there's going to be tests that we're going to need to quickly answer this question, which is a hard problem in general, depends a lot on the series, but there's one test that's very helpful, and you should always apply this test first. It's called the divergence test, also known as nth term test. And this says that suppose a given series n goes from 1 to infinity, an converges. If you knew that it converges, then you can deduce that the limit of the an's must be 0. Okay. It's very, very important to understand the direction of this implication. I'm saying, suppose we knew that this series converges, then the limit of the an's must be 0. Well, this kind of makes sense, right? Because if you're adding up infinitely many terms, like a1 plus a2 plus a3 plus a4 dot 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 forever, if this sum actually converges to some finite value, well, how could that be possible? Well, as a consequence of the fact that it converges, the terms that you're adding up at each iteration, at each term, must get smaller and smaller, in fact, must converge to 0. Now, divergence test is usually not applied in this way. It's applied usually in an equivalent way. So equivalent formulation, which is the one I want you to remember, which is the one that is often useful in practice, which is to turn this around, meaning that if you start with a sequence, is a sequence such that the limit of the ANs is not 0, such that limit as n goes to infinity of ANs is not 0. Now this could happen, either this situation would happen if ANs diverge to begin with, and there's no limit to begin with. So in fact, the limit can't be 0 because there's no limit. Or the limit of the sequence could converge, but to non-zero numbers. For example, the limit of the n's could be 0. Could be 7. So this is this hypothesis. Okay, this is the hypothesis we need to apply divergence test. So if you have a sequence such that the limit of the n's is not 0, then you can conclude that the series must diverge. The series must diverge. And this is what you have to remember, okay, when you're applying the divergence test. Divergence test does not say anything about the case when the ANs have limit 0. It's only saying that if you have a sequence such that the limit of the ANs is not 0, then the sequence diverges. Well, why is that the case? Well, because if the sequence converged, we know, if the sequence converged, then we know that the limit of the ANs is not 0. So if you assume that the limit of the ANs, if the sequence converged, then we know that the limit of the ANs must be 0. So if you know that the limit of the ANs is not 0, then you can automatically conclude that the series n goes from 1 to infinity of AN diverges. It's a very, very useful test, and this is what you should be applying first when you see a series and you want to test if a series diverges or converges. Apply this test. So big warning is that the divergence test can never be used to prove convergence, and that's why it's called the divergence test, because it can only be useful to prove divergence. The divergence test can never, I can't emphasize this more, can never be used to prove convergence of an infinite series, to prove convergence of infinite series. It only can be used to prove divergence, and it can only be applied if the limit of the ANs is not 0. Okay? So warning once again, if you know that the limit of the ANs is 0, then the divergence test is useless. Then divergence test is inconclusive, is useless. Anything can happen in this case. Can happen. We need more information, basically. Anything can happen. We need more tools. So we actually already saw a phenomenon like this before. So if you look at sum 1 over n, as n goes from 1 to infinity, versus sum n goes from 1 to infinity of 1 over n squared, right? So in both cases, limit of the ANs is 0, because in both cases, limit of the ANs is 0, but one of them diverges, one of them converges, right? So in both cases, the limit of the ANs is 0. So here AN is either 1 over n, or AN is 1 over n squared. In both cases, the limit of 1 over n or 1 over n squared is 0, but one of them diverges, this one diverges. This series diverges, and this series converges. This series diverges, and this series converges. So you see, we can't actually conclude anything from the divergence test. The series could diverge or converge or diverge. So the the divergence test is only useful if the limit of the ans is not 0. Okay, so example, if you look at n goes from 1 to infinity of cosine 1 over n, let's determine the convergence and divergence of this series. So let's look at an. An is the nth term, so this is cosine 1 over n for this particular series. Note that the limit of the ans, in this case, well, we're computing the limit as n goes to infinity of cosine 1 over n. So because cosine is continuous, we can actually interchange the limit and the function like so. Here we're using continuity of the cosine function to be able to interchange the limit and the function. Now this is just cosine of, as the limit n goes to infinity of 1 over n, this converges to 0, so we just get cosine 0, which is 1. Okay, so what did we just show? Oops, sorry. So we just showed, so the limit as n goes to infinity of ans is 1. So it's not 0. So divergence test can be applied. Divergence test implies that the series must diverge. Diverges. Done. See? Once the limit of the ans is not 0, the series, the corresponding series diverges. Here's another example. Let's determine convergence of the series. N goes from 1 to infinity of 3n squared plus 5n plus 7, 8n squared plus 1. This is the square. Okay. Again, solution. So convergence, by determining convergence, I mean determine convergence or divergence. So we have to figure out which one is it. Divergence. Oh. Okay, again, the solution, the sequence that corresponds to this series is the thing in front of the sigma. So 3n squared plus 5m plus 7 divided by 8n squared plus 1. Now note that the limit as n goes to infinity of ans is just the limit as n goes to infinity of 3n squared plus 5m plus 7 divided by 8n squared plus 1. Now, this is a ratio of two quadratic terms, two quadratic polynomials with, so leading coefficient 3 and 8. So the limit is just the ratio of these leading terms, because as n gets larger and larger, the 5m plus 7 and the 1 will be negligible, so everything is determined by the leading term. So in particular, 3 over 8 is not 0. So divergence test implies that divergence test implies that the series diverges. Once the limit of the ans is not 0, the corresponding series, n goes from 1 to infinity, of 3n squared plus 5n plus 7 divided by 8n squared plus 1 diverges. So this is where I'm going to end the lecture, but again, I want to emphasize one last time that divergence test, if it's applicable, can only be proof divergence. So if in your solution you say limit of the ans, blah, 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 and something converges, that means you did something wrong. So if the limit of the ans is not 0, then the divergence test can be implied. It can be used to show that the corresponding series diverges. And if the limit of the ans is 0, then the divergence test is not applicable. Okay? If the limit of the ans is 0, divergence test tells you nothing. Okay, so here's where we're going to end the lecture 21.